And, yeah. We'll start here tomorrow. Okay, so what we're going to do is add all of those up. And if it's a complete probability model, it's going to add up to 1. Is everybody with me? Mm-hmm. Can somebody help me out? Because we're going to be checking lots of probabilities today. So if you don't have your calculators out, it might be helpful for you to take them out. Okay? And what are we thinking?
Yes,
it does in fact add to 1, so we can say, yeah, this is a complete probability model. This is everybody in this service group. Cool? All right, now, they're labeling the traditional college age to be 18 to 23 years old. What's the probability that someone is not 18 to 23? How'd you get that? 1 minus 0.57. And guys, rule of thumb, probability is one of those areas where kids stop showing their work. I don't know why you guys stop showing your work, but it happens, okay? Don't write down a number that I didn't tell you without showing me where it comes from. Does that seem like a reasonable request? And we get 43%. Could we also have just added those 3 together? Sure, and I would totally accept that as long as you showed 0.17 plus 0.14 plus 0.12. How are we feeling so far? Good? All right. So, Nika, we're on the bottom of the next page. All right. Mutually exclusive events. 2 events are considered mutually exclusive if they can't occur at the same time. What are some examples of events that can't occur at the same time? I'll start. I pull up to a stoplight. What is the probability that that stoplight is both red and green? 0. It can't happen, yeah? Everybody good? What are some other events that might be considered mutually exclusive? Freshman and senior. If I randomly select a student, can they be both a freshman and a senior? Does this make any sense? All right. And so whenever, also we have, I'm going to start introducing some symbols, okay? Do you guys notice that I'm describing my events in capital letters? Okay. That's very, very common. And we also use some, they're called set notation symbols, okay? The word and is typically represented by an upside down U, which is technically called the intersection of 2 things. I remember that one's and, because if I imagine a dotted line here, it makes an A. If that's helpful. How you guys feeling so far? Okay. Oh. So notice again, this is just defining these two events A and B. Yeah? Are they mutually exclusive? Prove it.
Well, one person can't have the same cholesterol.
Okay, so there's no overlap between the ranges, right? Because like if A had been 230 or above, they would not be mutually exclusive, right?
Right.
Okay, so there's no overlap, and a person can't have two cholesterol levels.
No overlap and
A person can't have no overlap in ranges. Like when you look, if something's bigger than 240, it's not in between 200 and 239. Okay. Is everybody good? And knowing that they're mutually exclusive, if I asked what is the probability of A and B, you would say? 0. It isn't happening. Okay. Now, if I asked you in like context, that's what I mean when I say in plain language, what does A or B really mean?
Person's level cholesterol.
The person's cholesterol level is what?
is if they have like high cholesterol or borderline high?
Is high or borderline high. Okay. How would you guys feel if and I'm just going to put this in parentheses, more than 200? Or 200 or above. Does that fit here? Is that you? And what's the probability of that? Nah. Oh, sorry guys, here. Did you guys see this? I didn't point this part out.
Oh.
That cuz listen, if we said 1, what would that imply? Everybody has high cholesterol. Does everybody have high cholesterol? No. Cool? Okay, so the probability of A is 0.16. The probability of B is 0.29. And if those two events are mutually exclusive, I can just combine them and say, hey, the probability of A or B is 0.16 plus 0.29, which is in fact equal to 0.45.
Yeah.
I'm not very good with numbers.
Yeah. Well, so why wouldn't you use the and symbol?
Because and what is the remember I said what is the probability of A and B? You guys said it was 0 because they're mutually exclusive. There's a difference in meaning between the words and or. We comfortable? There's going to be a lot of times where I ask you guys to give me like a 1, well, not a thumbs up one, but like a 1 if I don't understand something and a 5 if I totally get something, because this is a pretty pivotal lesson today. Cool? So don't get irritated with me. I just care about you a lot. Yes?
So if it's the upside down one, that's and if it's a
Yep.
U, that's or. Okay.
And we have one more coming. 2 more coming. 2. Okay. So guys, last question. we're going to let C be normal cholesterol, below 200. What is the probability of C?
1 minus 0.45.
1 minus 0.45. Because if you either have high or you have normal. This encompasses everybody. Yes? And I'm not good with numbers, but I'm pretty sure that's 55%. All right. Remember that time I said, I care about you guys a lot? I'm about to completely lie to you, and I did it out of caring for you, okay? This whole table of data is a lie. You want to know why? I thought there was by the way, beard and mullet, you guys answered this question for me early in the school year. Beard is when your toilet paper looks like this. Oh no. I asked you guys, how do you think people should hang their toilet paper? Beard style? Or mullets? Oh no. I was good at this. I drew really good ones.
Over or under?
Yeah, over and under. I just like calling it beard and mullet because I think it's hilarious. Because, like, this is like somebody with a mullet. And this is like somebody with a beard.
Beard.
Don't laugh at me.
Okay.
Everybody good? And here's the deal. I thought for sure, in my own head, my intuition told me that somebody who has a pet, like one of my pets, who likes to go like this on the toilet paper roll, would use the mullet style. Because if you use the mullet style, that doesn't unroll all the toilet paper, but if you use the beard style, it does. And I was wrong, which is a great example of how just because we think a relationship exists doesn't mean that it does. And that's why this whole time is why we gather data to actually reinforce what we think. And we have to just, own it and accept when it doesn't. Cool? Everybody good? Now, here's a problem. The data that came from you guys ruined how I was going to use it instructionally. You guys get what I'm saying here? So, I'm lying to you. This table is a lie, but I'm doing that because I care about your learning. And I want to make sure that the table does what I need it to do instructionally, okay? So any relationships that we see, because we're going to dive into this a little bit more later on as well, any relationships we see, you guys, don't believe them. They are a lie, because Ms. Meister made up the data. I don't like doing that. I like using real data, but my first role is as a teacher. My second role is as a statistician, so full disclosure, I lied to you. But it's because I love you. Cool? All right, now, beard, mullet. So you notice that we're starting to use these like capital letters, and I'm going to introduce a new symbol here. I'm going to call this one B, and this one M, and usually that one's not a problem. I'm going to call this one P. I'm not going to call this one N. I'm going to call it P with a C up here. Does anybody want to guess what that C stands for? It's a word we talked about yesterday. It is complement. Because not having a pet is the complement of having a pet. So basically, whenever I describe something as know something, I usually use the complement symbol because I think it makes a little bit more sense. Okay? All right. So that C is my third extra symbol I'm adding to. There's going to be one more. Okay? All right. So if I randomly select a student, what is the probability that person has a pet and uses the mullet style of toilet paper? No. I like the 8 though. How would we just...
8 out of 56.
It's going to be 8 out of 56. Which works out to be 0.143. All right. Now, if we know that a randomly selected student has a pet, what's the probability they use the mullet style of toilet paper?
8 out of 41.
It's 8 out of 41. Do we see the difference? Okay.
Would we write it as like how you like the P?
So yeah, remember I said there's gonna be one more symbol?
Oh,
We
okay.
need one more symbol here, right? Because I can't just write P and M again, can I?
No.
That would be weird. It can't mean two different things, right?
14.3% again.
No, not at all. I don't know why I wrote that, you guys. It's definitely it's like, I think it's like
195.
195. Yeah, it's just under 20. So in this case, what do we have? We have the probability that somebody has a mullet, right? That's the probability. Uses a mullet toilet paper, given they have a pet. So the vertical bar means given.
So would you get points taken off if you like did P vertical bar M?
So let's look at the next question.
Okay.
All right. What if we know somebody has a uses, we know that a randomly selected, that should say student in there, uses the mullet style of paper, yeah? So now that means given that they use the mullet style of paper, what's the probability that they have a pet?
It's still 8 divided by 56.
8 over 11.
8 over 11. Because now, if I know that they use the mullet style of toilet paper, I know they're in that row. Does that make sense?
Yeah.
So, Maria, do you think it matters?
Yeah. That's probably.
Okay, one more thing before we turn the page here, okay? Y'all. If I were to describe, oh man, the 8 is essentially describing P and M, yes? How many people are P and M? The 41 is describing, this 41 is describing all of the P's. The 11 is describing all of the M's. Okay, is everybody still good? So in reality, this 8 over 41 is in fact P and M over P. And the 8 out of 11 is P and M over the M. So kinda, if we can get this idea of these given symbols, okay, the bottom of the fraction kind of comes after that vertical bar that almost makes me look at it as a denominator, kinda. But I don't want you to think as the first one is the numerator. How are we feeling so far? 1, 2, 3, 4, 5. 1 is terrible, 5 is great.
3.5.
Okay. Next to what we did here to begin with. Is this okay? Same. Oh, lovely. So good. This is what we call the general multiplication rule. By the way, those are what we call conditional probabilities. Okay? All right. General multiplication rule can help explain a concept that we started talking about yesterday, and I had you guys convinced eventually, but not really. Okay? You guys remember when I asked you, like, what's more likely to happen? Heads, or heads, tails, or whatever? You guys remember that question? Okay. So if I want to find the probability that two events occur, I find the probability of the first event times the probability of the second event, given that that first one occurred. So let's say I have heads and then tails. Is everybody with me? What's the probability of my first coin? So if I want to find the probability of heads and tails, what's the probability that the first coin is heads? 0.5. What's the probability that the second coin is tails, given that that first coin was heads? It's still 0.5. So that probability is 0.25. And in our heads, no pun intended, okay? In our heads, we think, oh, if I'm flipping two coins, I should get one heads and one tails. So that should be more likely than heads. But hey, guys, what's the probability that that first coin is heads? 0.5. What's the probability that the second coin is heads, given that the first coin was heads? Oh, look. They have the same probability. Everybody good? Does this kind of help make sense of some of that stuff? All right. Let's say I'm randomly selecting two students from this room right now, and I say, what's the probability that I get glasses and glasses? Everybody good? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 10 of you in here today. Everybody good? Looking around the room, I'm randomly selecting two of you. Yes, what's the probability that the first one wears glasses? 3 out of 10.
But do contacts count?
No, I'm going with glasses. Okay? Now, to find what's the probability that the second person wears glasses, given that the first person does? 2 out of
9.
But I would multiply those probabilities. So the coin flips, it's easy because the probability never changes, whereas now the probability does change. And we could still get an answer. We get 6 out of 90, which works out to be 1 out of 15.
Can we leave it as a decimal or a fraction? Okay.
But does this make sense in terms of this general multiplication rule? Okay. Now, if the probability of A and B is equal, I'm going to super zoom in on this because I don't want to get distracted by everything else. If the probability of A and B is equal to the probability of A times the probability of B, given that B is, well, what that says. Mm-hmm. Okay. And we just figured out that rule is true, and did that make sense to you that you would multiply those probabilities? Okay. So what if I wanted to come up with a formula that tells me what is the probability of B given that A has occurred?
P of A and B over P of A.
That if I wanted to get that probability of B given A by itself, I would just divide, yeah? So if I want to find the probability of B given A, I just do the probability of A and B over the probability of B, which y'all...
Wouldn't it be the probability?
No, probability of A, that's what I said. It'll make sense in a second. Okay, why I made that mistake. Okay. Guys, do you see how that... All right. I'm going to have another sip of coffee. Let's make that too. When you guys take the AP test, and we're at the point where I should really make them, For the first few units, the formula sheet that you get on the AP exam serves more to disturb you than to help you, okay? Because it has all the formulas for calculating standard deviation by hand, which you guys won't do because you all have calculators, yeah? So I just haven't given them to you yet. It also has probability formulas, okay? One of the formulas on that formula sheet says that the probability of A given B is equal to the probability of A and B all over the probability of B. I will never ask you to memorize this formula. I will ask you to use your formula sheet as a resource where you have this formula. Seem reasonable? Okay. Now, I got to paint a picture for you, okay? These are actual data from the Beijing Olympics, but this was like the 2008 Summer Games. Okay, so it was a while ago. You guys were like 3 or 4. Okay, so I should probably update these. Yeah. When I first started teaching, everybody remembered the Beijing Olympics. Okay, so I want you to imagine you've worked your entire life to get to the Olympics, right? For the athletes at the Olympics, are you guys in agreement with me that that is probably one of their life goals? Mm-hmm. Okay. You're getting ready to compete. You do the thing where they make you pee in a cup, right? They give you a drug test, and you test positive. Everybody good? Think about that like in an emotional sense. Like when I think about that, it makes me like terrified. Like it brings a sense of anxiety that is gross, right? You guys get what I'm saying here? Okay. Is everybody who tests positive actually using performance-enhancing drugs? Definitely not always. So in some respects, you're that person. Wouldn't you want to know, well, since these tests aren't perfect, what's the probability that I took drugs given that I tested positive? You guys with me? That's something we might want to find. Cool? All right. And if I were to try to apply this formula to that, what would the top of my fraction look like? D and P over P. You guys with me? Now let's try to make some sense of this, okay? All right. So suppose that 2% of athletes actually have taken banned drugs. Good so far? What is that really telling us? That the probability of taking the drug is 0.02. All right, so then I'm going to say, well, what's the probability then of D complement? 0.98. All right, what's the probability? So what would a false negative really mean?
They took the drug, but it says negative.
They took the drug. All right, so that 0.5% is essentially the probability that they tested negative given that they took that drug, yeah? That's that 0.005. And likewise, what would a false positive be? That 1%. Well, that would be, that would mean they didn't take the drug. So given that they didn't take the drug, what's the probability that they tested positive? That would be 1%. I'm going to sit back for just a second, let you guys look at that and tell me how you're feeling.
So why, for that equation, to my right, why is it over P when the other one up here is over A?
Well, so
Or like, I guess I'm just confused because on the like equation up here, the A goes to the first spot
Okay,
above.
the given.
Yeah.
Oh, I see what you're saying.
But it goes.
So
to
A and B and A, same
we
thing.
switch. Okay.
They're the same thing, so it doesn't really
So
matter.
we should we just ignore the top one? Yeah. Okay.
All right, now, my favoriteest probability tool in all of the stuff you will learn from me, my favorite probability tool is called a tree diagram. It's not my favorite because it's the easiest. It's my favorite because when I get stuck, it's usually the thing that helps me. Does that make sense? So, a tree diagram goes like this. To build a tree diagram, we say, what's the first thing we know? We know the rate of the person took drugs or didn't take drugs, yeah? So I'm going to start with branches that say drugs and drugs complement. And on each of those branches, I'm going to put those probabilities. All right. Now, the other things we know are those conditional probabilities. What if I know that somebody took drugs? Well, that is this number right here. They're either going to test positive or negative, right? What's the probability they test positive? That would be they test negative is 0.005, right? So what does that make the probability they test positive? 0.995. And the minute I see, if I can attack that this is given D, I can start traveling down the D branch to create this new branch. And then this other one, given D complement, tells me I'm on this branch, and it gives me information. Okay? And that's what conditional probabilities are hard because we're trying to sort through this stuff. And I think that tree diagrams make it really easy to sort through what's going on. Okay, so the probability of positive is 0.01, which makes the probability of negative 0.99. Now, here's the other thing about tree diagrams. Has this told me the entire list of possibilities? What's another possibility?
Oh, wait.
Are there any outcomes that are not somewhere on this tree diagram right now?
No.
No. Cool? And what happens is I can find the probability of each branch using that multiplication rule. Okay? So the probability of this branch is going to be 0.02 times 0.995. Just so you get 0.0199. Yeah. Okay. This one would be 0.02 times 0.005. And it's pretty unlikely, by the way. Can I ask you one more question real quick, y'all? If I add those two together, what do I get? I don't get 1, right? Are we all cool it's not 1? I get 0.02. Does that make sense that I would get 0.02? That's describing all the people who took drugs, right? Is this okay? What about over here? I can do this one. I'm good at that one. And then from there, I think I can get 0.9702 because those two have to add up to 98%. All right, so of all the people that took this drug, or took this test, sorry, that took this drug test, what percent tested positive?
Would it be 0.098 plus 0.0199?
We would say, hey, my positive branches are these two, yes? Those are the ones that are positive. Is this okay still? Oh, man. So 0.0199 plus 0.0098 and 0.0297. All right, so we had just said, using this formula, that the probability of D given P is D and P over P. We're all good with this, yes? So if I want to find this probability, what do I put at least on the bottom of my fraction? 0.0297. Because we only need to look at the 2.97% of people who actually tested positive. All right, now, what number on this describes both took drugs and tested positive? Well, I would start here and say, took drugs, and then they tested positive. They get this number, the 0.0199. And I believe it works out to be 0.67.
Mm-hmm.
Okay. Now, because this is statistics and we never stop caring about the context, I want to go back to that emotional place we were, where you got to your life goal, you tested positive, and only 2 in 3 of the people who test positive actually took drugs. So there's a 1 in 3 chance that you didn't take drugs. How do you guys feel about that?
Kind of icky.
I feel really icky about it. I would feel like, what? Do you guys get what I'm saying here? So here's the deal. You never hear about somebody tested negative for drugs or tested positive for drugs. You hear they tested positive for drugs multiple times. There's a reason they give athletes many, many, many drug tests, and not all of it is not all of it is about the longevity. Like, because like at the elite levels, they test every 3-4 weeks, right? And that's about we can't just test them once because they'll just wait until they've tested clean and then they'll, Some of it is at the Olympics. They usually every day make you do it. And that one is not necessarily about anything other than, and when you test positive, they make you test again. And that's why athletes have the ability to appeal and say, no. And this same kind of rule can apply to COVID tests, flu tests. Pretty much any medical test has some false positive and false negative rates. And you guys look at these ones and you're like, wow, those are really good false positive and false negative rates. I agree. So imagine when the test isn't like that. Those good rates. Cool?
Yeah.